Earth in Space, reading page 98, Our Sun's Energy. The Sun may be only one star among billions of other stars in the universe, but it's the one that makes our life on Earth possible. How? The Sun provides us with energy that gives us solar power, fossil fuels, waves, and surface wind. Without heat and light from the Sun, Earth would just be another dark, cold planet in space where life as we know it could not exist. Where does the Sun get all its energy? It all starts with its size. The Sun's mass is enormous, approximately 300,000 times greater than the Earth's. The more mass an object has, the greater the pressure at its center due to the force of gravity. And when gas is squeezed or compressed, it becomes hot. Most of the Sun's mass is composed of hydrogen gas atoms. Physicists came up with the hypothesis that the Sun's tremendous mass squeezed the hydrogen atoms until they fused and released the heat and light energy that reaches Earth. Page 99. Think about the hottest oven you can imagine, and then turn up the temperature to about 14 million degrees Celsius, or 1.4 times 10 to the 7. That's how hot it gets in the center of the Sun. At that temperature, the hydrogen nuclei, or centers of each hydrogen atom, are moving so fast that when they crash into each other, they stick together to form helium. The result of the crash of hydrogen nuclei is a tremendous amount of energy, released mainly in the form of heat and light. This reaction is called nuclear fusion. Scientists calculate that there is enough hydrogen in the Sun to continue the fusion reaction and provide heat and light energy for at least another 5 billion years or so. Solar energy. Energy from the Sun is called solar energy. Solar energy is the source of most of the heat on the Earth's land, in its oceans, and in its atmosphere. This energy makes its way through the vacuum of space to Earth by a process known as radiation. Radiation is often identified by the effect it produces when it interacts with an object. Some solar radiation is visible as light, 43%, but not all solar radiation can be detected by the human eye. Infrared radiation, 49%, cannot be seen at all, but we can detect it as heat. Another type of radiation is responsible for the sunburn that can occur after exposure to the Sun. Scientists call that ultraviolet radiation, which makes up 7%. Gamma rays, X-rays, microwaves, TV waves, and radio waves make up the remaining 1%. Solar energy is important to life on Earth, but surprisingly, most of the Sun's energy does not reach Earth at all. It travels out through space in all directions. Earth's land and oceans absorb about half of the small amount of solar energy that reaches us. The rest is reflected back into space or absorbed by the thin blanket of air, the atmosphere, that surrounds Earth. The interaction of solar energy with air, soil, and water on Earth creates our weather. The uneven heating of the Earth causes wind, rain, and other elements of weather and makes our planet unique and habitable. Page 100. Our atmosphere and life on Earth. Earth's atmosphere protects our planet. How? The atmosphere keeps us from receiving too much solar radiation. The tilt of the Earth on its axis and the Earth's rotation help vary the amount of solar energy that reaches any one place on our planet at any time. Too much of the Sun's energy, too much ultraviolet radiation, for example, would be harmful to life on Earth. Like a blanket, Earth's atmosphere also helps keep our planet warm at night. And most meteors and other rocks from space burn in the atmosphere before they reach the Earth's surface. Our planet receives just the right amount of solar energy to sustain life. If Earth were just a little farther away from the Sun or just a little closer, life as we know it probably could not exist. Page 101. Solar energy on other planets. Planets get most of their energy from sunlight. If all conditions were the same, the closer a planet is to the Sun, the warmer that planet should be. But this is not always the case. The temperature of each planet depends not only on the amount of sunlight that strikes it, but also on the way that the planet's surface returns infrared radiation into space. The way a particular planet absorbs the sun's radiant energy depends on its atmosphere. For example, Earth's atmosphere reflects part of the radiation back into space and distributes heat from the sunlit regions to the cooler poles and to the side facing away from the sun. Without its atmosphere, which is made up mostly of nitrogen and oxygen, the temperature of Earth would be nearer to negative 260 degrees Celsius and the oceans would freeze. The climate of Venus is very different from the Earth's, even though Venus is similar to Earth in size, mass, density, and distance from the Sun. Its atmosphere is made up of 95% carbon dioxide and trace amounts of water vapor. This mixture lets in visible light from the Sun but does not release the infrared radiation generated by its hot, rocky surface. This greenhouse effect makes Venus extremely hot, with surface temperatures that can reach 482 degrees Celsius. Mars also has an atmosphere that is made up of 95% carbon dioxide. But because Mars' temperature is always below freezing, its water vapor is frozen in the planet's polar ice caps and soil. Without water in the atmosphere, most of the Sun's energy that reaches Mars returns to space. In addition, the Martian atmosphere is so thin that it cannot block the deadly ultraviolet rays of the Sun, greatly reducing the greenhouse effect as compared to Earth or Venus. The end.